In the previous podcast, we showed how we can obtain an analytical solution for the horizontal infiltration problem in a homogeneous dry soil from a wet surface. In addition, with the Python notebook, we were able to calculate the water content profiles for different time intervals. The direct possible application of this model is therefore to simulate water content profiles for different values of diffusivity d, space x, time t, saturated water content theta s, and initial water content theta I. This solution that we presented in this previous podcast is, however, limited to the case where the diffusivity d is constant. Yet we know, as seen in previous Python notebooks, that the diffusivity d in general is a function that varies significantly with water content theta. The hypothesis of a constant d, as considered in previous podcast, is therefore very unrealistic. In this podcast, we show a more practical application, where we consider the horizontal infiltration from a wetting surface, but in which we consider that d is no longer constant. This will result in a method for determining the diffusivity d as a function of water content theta for a real soil. In previous podcasts, we used the Laplace integral transform to reduce the dimensionality of the problem. In this podcast, we use another transform to reduce the dimensionality of the flow problem, the Boltzman transform. The problem that we analyze is similar as compared to the previous problem. We consider the horizontal infiltration into dry soil from a well. And similar as in the previous podcast, we use the Fokker-Planck equation in order to formulate our flow problem. And we define exactly the same initial and boundary conditions. The only difference that we have is that we consider a variable diffusivity d. The Boltzman transform that we use in this podcast is a mathematical trick to combine space and time in one single variable eta, which is defined by the ratio between x and the square root of time. We calculate the time derivative of eta using classical calculus and also the space derivative. And with these derivatives, we rewrite our transport equation. We can apply the previous formula to the left and right hand term of our transport equation, and this results in a new formulation of our transport equation, but now in terms of eta. So we combine the space and time in the new variable eta. Of course, we need also to transform our boundary and initial conditions in terms of eta. This gives us the following results. We can now use this transport equation in eta to develop a procedure to estimate the diffusivity d for a real soil. We start with our transport equation that we have integrated already the first time over dE theta, and that we rewrite now the right-hand term as shown in this equation. Now, in this right-hand term, we consider that the last term here is close to zero. So that means that we actually consider that the water content will not change a lot when we are approaching theta I, the initial water content. So if we do that, then we come up with this equation, which allows to isolate dE theta. For determining now d, we need to carry out a horizontal infiltration experiment. This means that we need to set up a horizontal column and determine the infiltration front as a function of time. This can be done, for instance, by installing soil water sensors in a horizontal column, allowing to monitor the horizontal infiltration in the soil. Subsequently, we can plot the soil water content in terms of the Boltzman transform eta. If we have this curve, we can calculate the slope of the curve for each value of soil water content. And we can also calculate the integral part below the curve for each soil water content. Finally, if we take the ratio between those two functions, we will obtain nearly the diffusivity. We see therefore in this podcast a direct application of analytical solutions of transport equations. If we set up in the laboratory or in the field flow experiments, subjected to rather simple boundary conditions, we may look for analytical solutions that describe such a simple experiment. If such an analytical solution exists, we can apply it for determining, for instance, the unknown system parameter, as in this case, the unknown soil hydraulic diffusivity. This is a nice example where analytical solutions are used in an inverse mode for determining hydraulic properties of soil. We come back to the inverse modeling of flow processes later on in this course. But before going further, have a look to the next Python notebook where we develop a nearly closed form expression for the horizontal infiltration into the soil.